Okay, so let us have a look at the Mathematica file, which is available on LMS, to see how this scheme works for the slider crank. Okay, so first we have the definition of the coordinates. So for the slider crank, we choose conveniently theta 2, theta 3, the coupler angle, and xc, the position of the slider, right? A dependent set. Okay? Then we put in the constraint equations in x and y directions, right? So we present constraints always everything on the left, 0 on the right. Right? So this is the vector closure equation projected on x-axis, and this is the vector closure equation on y-axis. And then we can set up our equation. So, as I said, left-hand side containing everything equals to 0. So this double equal sign creates an equation, and single equal sign assigns the value. So the variable EQX becomes this equation, right? So this is all symbolic, right? So it's the same for y direction, and then we solve. Okay? So here we are solving the initial assembly problem, or the position problem, right? We have our system of equations, EQX, EQY, and we are assuming theta 2 to be the input, so theta 2 is known, and we are solving for unknown theta 3 and xc, and in fact it is xc that interests us most, right? So this sort of should be making sense. You have mobility 1 mechanism with 3 generalized coordinates and two constraints, so 3 minus 2 is 1. Okay? So we get some warning messages here because it's a nonlinear problem, and in principle we may get some strange results, but here we get 2 solutions. Why 2 solutions? Do they make sense? Both of them, or only one of them makes sense?